So in this video, we're going to introduce sigma or summation notation, which is a shorthand notation for writing a sum. So in mathematics, if you have a sequence of terms separated by commas, we call this a sequence. And then if you take that sequence of terms separated by commas, and you take their sum, so a1 plus a2 plus all the way out to add the nth term, then we call this a series. And when we want to take the sum of a sequence or a series, we want to use a shorthand notation called sigma notation or summation notation. So this symbol right here is sigma, is just the Greek uppercase S. So it's an uppercase S. So we use S because it represents sum. And we have an index of summation. So this is a variable that you use to describe your summation. And the variable name doesn't matter, so it's very common to use I. Probably the letters I, J, K are the most common, but you can use any variable name that you want. And the variable is called the index of summation. And then you have a lower bound of summation and an upper bound of summation. You may or may not know the number that goes on the upper bound. So we represent it with an N here, but you can replace it with specific numbers when you need to. And all you do to do these is you go through and you plug, first starting at 1, you plug it in for I, so you get a sub 1. And then you increment this number. So if it starts at 1, you then add 1 to it to get a second term in the series, and you plug in the 2, so you get plus a sub 2, and it's a sum, so you're going to separate terms in the series by summations. So we've got upper and lower bounds of summation. We have an index or variable of summation, and we have the Greek letter S representing a sum. So here's how this plays out in practice. So we're going to go through a sequence of 4 examples. So this first one says take the sum, S for sum, take the sum from I equal 1 to 4 of I. And what you're going to do then is you're going to start with the number 1, and then you're going to increment the 1 to get a 2, and then you're going to increment the 2 to get a 3, and then you'll increment the 3 by 1 to get a 4. So you're going to plug the numbers 1, 2, 3, and 4, the numbers 1 through 4, in for the index of summation separated by sums. Usually you wouldn't write these terms up here. I'm just doing that for presentation purposes. So you start off with a 1, and everywhere you see the index of summation, you replace it with the number 1. So I see an I, so I'm going to replace I with 1. And because we're taking a sum, remember this is S for sum, you put an addition sign. Then you increment the index of summation by 1. Increment means add 1 to it. So you get a 2, and then you plug the 2 in where you see the I, and then you put an addition, and then you increment the 2 to get a 3. You plug 3 in for the I, so you get plus 3, and then you put a summation, and then you increment the 3 to get a 4, and you plug the 4 in for the I, and once you get to this upper bound, you stop incrementing the number, and you take the sum of the terms that you have in the series. So notice that we got 4 terms in this particular series, and in general what's going to be true is that if you take the upper bound of summation, the 4, and you add 1 to it, and then you subtract the lower bound of summation, which in this case is a 1, that will tell you the number of terms you expect to get in your summation. So I had 4 plus 1 is 5. 5 minus the lower bound of summation, so 5 minus 1 is 4. I expect 4 terms in my series, and then it's just a matter of simplifying the series. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. So the second example here says start at 2 and increment until you get to 5. So we're going to start with the number 2. We'll increment it by going 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. There's going to be 4 terms in this series that when we add them up. And I know the other way I could figure this out ahead of time is I could take the 5 and add 1 to it, and then subtract the lower bound of summation, which is a 2. So I get 5 plus 1 is 6, minus 2 is 4. I'm expecting 4 terms in my series. So I'm going to take the sum from I equal 2, the lower bound of summation. I guess I'll just use what I have here. I hate doing that without rewriting it. So what you're going to do is start with the 2, plug the 2 in everywhere you see an I. So we're going to get 2 minus 1. Once we plug in the 2, we put the add, and then we increment 2. When we increment 2 by 1 unit, we get a 3. Everywhere we see an I, we plug in the 3, so we get 3 minus 1. And then we go plus, and then we increment the 3 to get 4. Everywhere we see an I, we put in the 4, so we go 4 minus 1. Plus, we increment the 4 to get a 5. Everywhere we see the I, we plug in the 5. We subtract the 1. And then we simplify. So we get 2 minus 1 is 1, plus 3 minus 1 is 2, plus 4 minus 1 is 3, plus 5 minus 1 is 4. And then we'll notice that this is actually exactly the same series that we had up here. 1 plus 2 plus 3 plus 4. 1 plus 2 plus 3 plus 4. So we know when we add that up, we get a 10. So this particular example was chosen to show you that two different looking summations, each of these summations look different than each other, but two different looking summations can generate the same series. 1 plus 2 plus 3 plus 4 in this case. So another example, we have the sum from I equal 2 to 4 of 3i squared. So I'm going to rewrite the summation. We're taking the sum from I equal 2 to 4 of 3i squared. I expect to get the upper bound of summation is 4, plus 1 minus the lower bound of summation is 5 minus 2 equals 3. I expect 3 terms in my series. I'm going to be starting at 2. I'm going to plug a 2 in, then I'm going to increment the 2, which will make it a 3. And then I'll increment the 3, which will make it a 4. And when we get to 4, the upper bound of summation, we stop. So plugging first the 2 in everywhere we see an I, we get 3 times 2 squared. And then we go plus. And now we increment the 2, which becomes a 3. So we get 3 times 3 squared. And then we go plus. And then we increment the 3 and get a 4. 4 is the upper bound of summation, so this is the last number we plug in. So we get 3 times 4 squared, and then we need to simplify. So notice that the 3 showed up in all 3 terms. I could actually factor that out, and I get 2 squared is 4, plus 3 squared is 9, plus 4 squared is 16. So this would be 3 times 4 plus 25. This is 3 times 29, which is going to be 3 times 20 is 60, plus 3 times 9 is 27, adds up to 87. So there's that summation. So one more example, oh, 2 more examples actually. So this one, we're picking this one because it's starting at 0. So how many terms, and the upper bound of summation is n, which means I don't know where it's going to stop. It's going to stop at some counting number n. So what I'm expecting is to get n plus 1, take the upper bound of notation, add 1 to it, subtract the lower bound of notation, which is 0. N plus 1 minus 0 is just n plus 1. I expect n plus 1 terms in the series. So the first term is going to be a 0. Then we're going to increment 0, which will get a 1. We'll increment 1, which will make 2. And we'll need to continue this until we get to n. And when we get to n, we're going to stop. So first we plug in a 0. So I'm going to get 1 over 0 plus 1 is 1 plus the 2 that's sitting there. And then I put my addition, and then I increment 0 to get 1. I plug 1 in. I get 1 plus 1 is 2 in the denominator, so I get 1/2 plus I get the 2 again, plus increment 1 to get 2. 1 over 2 plus 1 is 3. 1 over 3 plus 2 is the next term. 1 over 3 plus 2. And because I don't know where I stop, I need to recognize that there's going to be an unknown number of terms in this series between this third term, 0, 1, 2. 2 corresponds to the third term in this series. There's an unknown number of terms in here. So I'm going to go plus dot dot dot. I know I'm going to end when I get to n. So when I get to n, I'm going to plug in 1 over n plus 1. So I get 1 over n plus 1 plus the 2. And I could reorder this. So I could say, look, I get fractions 1 over 1 plus 1 over 2 plus 1 over 3 plus there's going to be n plus 1 fractions because there are n plus 1 terms in this sequence. This sequence has n plus 1 terms in it. So I can take the n plus 1 fractions that I have, dot, dot, dot. There's an unknown number of fractions plus the last fractions 1 over n plus 1. So I can group the fractional terms together using the commutative and associative properties of addition, letting me reorganize things. Plus, I'm going to get a bunch of 2's added up. I'm going to get 2 plus 2 plus 2 plus, there's a whole bunch of 2's ending with this last 2. And notice I actually know how many 2's there are because there are n plus 1 terms in the sequence. That means 2 shows up n plus 1 times. There are n plus 1 2's, just like there are n plus 1 fractions sitting here. So I could actually simplify this again. I could say, well, this is 1 over 1 plus 1 over 2 plus 1 over 3 plus dot, 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 plus 1 over n plus 1 plus, hey, this is just a repeated addition. I'm adding 2 to itself n plus 1 times. So this is the same as n plus 1 times 2. And that probably this is a Calc 1 class, and based on what we've done so far together, this is probably as good as we could get in terms of simplifying it. This will actually simplify, but we don't have the tools in our pocket to simplify this at this time. So I'd say we can leave it here, and that's good. Now the last example is just to show you I don't need to know what the function or expression is in here. I could just say, hey, it's some function g of I, a function g of I, and here's times delta x, and we've seen delta x this semester a lot. So I could say, well, what does this sum look like? I have the sum from I equal 2 to n. So I expect there to be how many terms? I take the upper bound of summation, I add 1 to it, and then I subtract the lower bound of summation right here. So n plus 1 minus 2. I expect this to have n minus 1 terms in the series. And it's g of I times delta x. So this is going to equal, we're starting the lower index here, starts at 2. And then we're going to increment it to 3 and increment it to 4. And we're going to keep incrementing it until we get to this upper bound of summation. So we'll stop when we get to n. So just start with the 2, plug it in everywhere we see an I. So we're going to get g of 2. Whatever g is, we don't need to know that. G of 2 times delta x. And then we go plus. We increment 2 to 3. We get g of 3 times delta x plus we increment the 3 to get a 4. We get g evaluated at 4 times delta x plus dot, dot, dot. There's going to be a whole bunch of these because we don't know what n is. We don't know what these terms are going to look like just yet. We know there's going to be n minus 1 of them, though. And when we get to n, that's going to be g of n times delta x. And what I want to notice here is that the delta x shows up in each of the expressions that are being summed. So I could actually factor the delta x out, which would leave me g of 2 plus g of 3 plus g of 4 plus dot 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 all the way out to the nth n minus first term, because there are n minus 1 terms, which is g evaluated at n. And that would be the best that we could do with this right now, because we don't know what the function g is. G of I equals what? We don't know. So it's simplified as much as we can get it. So that's just a basic intro to sigma notation.